Today I'm giving this talk on the unceded lands of the Wurundjeri people of the Kulin Nation. I pay respect to elders past and present and to Aboriginal and Torres Strait Islander people in the wider Melbourne community. As Em said, this talk is about all closed orientable 3 manifolds being central in trisections of 5 manifolds. And this work is joint with Stefan Tillmann. Heegaard splittings are a classical decomposition of compact orientable 3 manifolds into a union of 2 identical boundary connected sums of solid tori called handle bodies, whose boundaries are glued together via an orientation reversing homeomorphism. So here we've got 2 such handle bodies. So these things are solid, and we perform this orientation reversing homeomorphism along their boundaries and we glue it together. And this is building up some kind of compact orientable 3 manifold. And I'd like to acknowledge Sol Schleimer for correcting a previous image that I had here was incorrect. So thank you, Sol. Heegaard splittings can be viewed as a level surface of a Morse height function on the associated 3 manifold M, which is a piecewise linear map from our 3 manifold to the closed unit interval 0, 1, where the preimage of half is the Heegaard surface that's common to both. And the preimage of alpha for some alpha contains strictly within 0, 1 is a surface isotopic to the Heegaard surface, where the image of one of the handle bodies is equal to 0, half, the closed interval, and the image of the second handle body is equal to half 1. Gay and Kirby generalized Heegaard splittings to the trisection of smooth-oriented 4 manifolds M, with the notion of the Morse height function being expanded to the partition map F from the 4 manifolds to delta, which is a 2 simplex. So Gay and Kirby came up with this really nice generalization of this classical idea of Heegaard splittings. And Rubinstein and Tillmann generalized this even further beyond the scope of this current talk to piecewise linear N manifolds and multi-sections. But in this talk, we'll be considering purely trisections of piecewise linear 5 manifolds. So let M be a closed orientable connected piecewise linear 5 manifold. A trisection of M is a collection of 3 piecewise linear submanifolds, H0, H1, and H2, such that each HI handle body is piecewise linearly homeomorphic to a standard piecewise linear 5-dimensional 1 handle body of genus GI, which are GI boundary connected sums of S1 cross B4 with boundaries connected sum copies of S1 cross S3. The handle bodies have pairwise disjoint interiors. And so that means that our piecewise linear 5 manifold is the union of these handle bodies. The intersection of any 2 5 handle bodies is a compact connected 4-dimensional submanifold with non-empty boundaries, where the boundary of any 5 handle body is divided into 2 such 4 manifolds. And we have that the intersection of HI with HJ piecewise linearly collapses onto a spine of dimension 2. The common intersection of all 3 handle bodies is a closed connected 3 manifold called the central 3 manifold. And that is what this talk is primarily about today. So here we've got a picture, sort of a diagram roughly describing what's going on here, because I know this definition is a bit confronting on first appearance. So what's happening here is this is kind of like the higher dimensional version of what we were looking at before. So here we've got our handle bodies. We've got 3 of them, H0, H1, and H2. And they are all boundary connected sums of S1 cross B4. And they share their boundaries in common with the other 2, which is seen here in this diagram. So for instance, H0 shares part of its boundary with H1, and that's the pink part over here, for instance. And they have this common intersection, the central 3 manifold. Let M be a 5-dimensional piecewise linear manifold with a triangulation T. A tricoloring of T is a partition, P0, P1, and P2, of the vertices such that every 5-simplex contains 2 vertices in each set of the partition. So here we've got that a tricoloring determines the partition map phi, where delta is a 2-simplex. So this is an interesting way to color our 5-dimensional piecewise linear manifold. And this map is of great interest to us, this partition map phi. So we can ask, what is the preimage of, for instance, the barycentre of the 2-simplex under phi? What would that preimage be? Well, we could first consider restricting to a single 5-simplex and see what we get. If we consider all the triangles in such a 5-simplex, as I have labeled over here, that possess vertices of all 3 colors, we have 8 such triangles. And notice the labeling. This labeling is corresponding to the labeling here of this 5-simplex. So the preimage of the barycentre will contain, of this 2-simplex, will contain the barycentres of all these 8 tricolored triangles, but that won't be the complete preimage. It turns out that this extends all up to a cube. So notice the labeling again. So here we've got 0, 2, 4 corresponding to this 3-colored triangle, which is corresponding over here to 0, 2, 4. And that's this vertex over here. And notice that this vertex shares a red-colored edge with 1, 2, 4, and it's 0 changing to a 1 on this edge. So the colors of the edges of this cube correspond to the changing vertex, right? So if the changing vertex is red, that means we've got 2 different red vertices on this edge. And so then we have this red colored edge. And so notice also that all edges that are parallel on this cube have the same color, and edges that are perpendicular have differing colors. So the preimage of this barycentre of this 2-simplex is this cube. So that tells you that if we're thinking about this tricoloring, the preimage of the barycentre of the 2-simplex, when considered in terms of the entire piecewise linear triangulation, is going to be a whole bunch of cubes. But what happens if we look at the preimage of other things? Well, if instead of just looking purely at the preimage of the barycentre and we keep shifting down, we notice that we keep getting a cube until we reach the edge. And then we'll get the square. And the square on the bottom here, notice is colored with red and green, which corresponds to these 2 red and green vertices. The dual spine of delta consists of a vertex corresponding to the barycentre of delta, 3 vertices corresponding to the edges of delta, and edges emanating from the central vertex to the barycentres of edges of delta. A triangulation of M supports a trisection if there is a partition of the vertices defining a partition map phi such that the pullback of the squares is a trisection. So basically what this is saying is that if we have this partition of these vertices that are colored in a particular way, we are able to recover a trisection that we talked about previously under some strong conditions of the coloring. So basically what's happening is if we're able to choose a very particular triangulation of our piecewise linear 5-manifold in this situation, and a particular choice of coloring of these vertices, this tricoloring is actually giving us a trisection. So this is like a discrete way of describing a trisection. So remember in the partition map, we're mapping to the 2-simplex. And so now here we can see that when we divide our 2-simplex into these 3 squares using the dual spine, we have that the preimage of these 3 squares are those 3 handle bodies. And the common thing in the center, the barycentre here, the preimage of that is the central 3-manifold. And we discussed just previously that the preimage of the barycentre is going to have to be made of cubes. So that means under this construction, in terms of this partitioning and coloring of the vertices, the central three manifold is a cubed manifold. Okay, so we've seen already how we get the cube with the labeling corresponding to the triangles. Now we think of the vertices of the triangle as, the vertices of the cube as vertices, but remember they're corresponding to barycentres of triangles. And similarly, we have that the edges of these cubes correspond to tetrahedra with the same kind of labeling. Squares in the cubing correspond to pentachora, and the cubes, as we've seen before, correspond to the five simplices. So basically, these things are living within these n simplices. So this vertex is the barycentre of this triangle. This edge here that corresponds to 0124 is living inside this tetrahedra, right? One of its vertices lies at the barycentre of 024, and the other vertex lies at the barycentre of 124. So we have this really interesting correspondence between the different cells of the central cubing, the vertices, the edges, the squares, and the cubes, and parts of the outer triangulation. Okay, so we've talked now about how we can begin with a trisection and somehow understand parts of the central submanifold. But the goal of our approach is to go in reverse. So we begin with a proposed central submanifold, and hopefully we recover some kind of trisection. But this isn't something we can take for granted. We can't just pick an arbitrary cubing, in our case, a three manifold cubing, and just assume that this, and if we choose the right coloring, that we'll end up with a trisection. So this, it's not immediately obvious, but it's not always possible. So the following is an example of when it's not possible. So here is a description of the Seifert-Weber space, which we get by taking a dodecahedron and performing a 3/10 turn on opposing faces and gluing them together. If we take this dodecahedron and we apply a barycentric subdivision to it, this allows us to get a cubing. So this is a really convenient way to cube some kind of polyhedron. And so notice, as we talked about previously, that edges in a cube that are parallel have to have the same color. So we can play this kind of coloring game where we keep coloring all edges that are parallel to each other that are on the same cube, the same color, because they have to have the same color. And as we go around, because of this 3/10 turn, we end up with a coloring, if I repeat the animation, of two edges which are perpendicular, but have the same color. So they're forced to have the same color here. So there are choices of cubings which do not allow for a trisection. And also there are choices of cubings which would not permit three colors and have all the edges be colored, associated with these conditions of having parallel edges on the same cube with the same color. So we have to be a bit careful here with our approach of finding such a coloring. So here's the way we went about it. So we took advantage of the dodecahedron and we looked at the Borromean rings. So they're amazing. And so they satisfy a condition called being universal. So a knot or a link is said to be universal if every closed orientable three manifold occurs as a finite branch covering space of S3 with branch set the knot or link. So there's this amazing theorem of Hilden, Lozano, Montesinos, and Witten that states that every closed oriented three manifold is a covering of S3 branched over the Borromean rings B, such that the branching indices of the components are subsets of 124, 124, and 24 respectively. So this is a very powerful result because we're able to restrict these indices to a very small number of possibilities, and still we're able to recover every closed oriented three manifold. So let's talk a little bit in detail about these pictures here. So these are the Borromean rings. And what we can do is we can kind of embed them on a dodecahedron. So we take half segments of the Borromean rings So we chop these rings in half and put one of the edges of those halves on the edges of the dodecahedron as follows. And it turns out that if you you close it all up, which we'll see very soon, you get S3 with the the Borromean rings living inside of it. If you just close up, so here's an animation of that. So if we can close everything up, we end up with the Borromean rings. Okay, but so what's really important here when we're thinking about branch coverings is how do we go about actually calculating it? So here is the fundamental group of S3 with the Borromean rings removed. And so notice here that the generators of this presentation are A, B, C, which are the meridian elements here of these link components. And these relations are describing how the meridians and longitudes have to commute with each other. And there's a third redundant relation that's omitted here because it's sort of a consequence of the other two by symmetry. And so to get the branch covering, what we do is we take this fundamental group and we map it surjectively to some group, some finite group G. And the way we think about this finite group is as a subgroup of Sn, right? It's very convenient for us to think of this group G as a subgroup of Sn. And so the idea is that we're taking all these dodecahedra. So we've got, an ordered N branch covering. We have N dodecahedra, and we're gluing everything up. And the way we're gluing everything up is using the orientation that we've on the link components. So using the right rule with the dodecahedron. So for instance, this face over here will be glued to the next dodecahedron, but it will be glued to this face over here, right? So you can go through an example of how that works. Okay, so now we've got this idea of how we can get every single closed-oriented three-manifold, but the idea is we need to pick the right cubing to make this all work. So taking a barycentric subdivision turns out not to work. So we have to be very particular with the choice of cubing. So here is the cubing that we chose. It looks a little bit confronting, but if I talk you through it, you'll be fine with it. So the idea is consider just one of the pentagons on the dodecahedron. Just forget everything else, just look at one of the pentagons. Now notice that we have this black vertex in the middle, and what we're doing is we're taking this pentagon and we're subdividing it into 10 triangles that all share that black vertex at the center, okay? And so we've got these 10 triangles, right? So here's one of those triangles. So hopefully you can see the mouse there, right? So we've chopped this pentagon into these 10 triangles. And then we've placed a vertex at the in the barycentre of that triangle. And we think of this now as the corner of a cube. So now we have 10 corners of cubes on the outside that correspond to these divided triangles, right? And all of these cubes sort of are coned into the barycentre of the dodecahedron, okay? So we've got one corner of the cube on the outside over here, and the other corner of the cube is in the centre of the dodecahedron. So each pentagon has 10 such corners of cubes on the outside, which all cone into the barycentre of the dodecahedron. And the dodecahedron, it has 12 pentagons. So that means we have 120 cubes. So we've divided our dodecahedron into 120 cubes. On each pentagon, we have 10 such cubes with corners of each of these cubes on the outside and the opposite corner of the cube in the barycentre. And the colouring is chosen so that we get this kind of dihedral symmetry. So remember, we saw how we're gluing everything together. We're sort of doing these kinds of reflections. So this choice of colouring has to respect that reflection. So it's got a dihedral symmetry. And it's respecting the condition that, in a cube, edges that are parallel have the same colour. Okay. So here is those conditions into that a vertex corresponds to a triangle and the outer triangulation and so forth. So the coloring, this choice of coloring and the cubing is determining all the information about the outer triangulation. So it's really, as soon as I've chosen what one of these things is, as soon as we've chosen the choice of labeling of one of these cubes, and we keep going with some kind of choice of labeling, and we like that choice of labeling to allow for an oriented gluing, which is convenient for us, everything is determined up to labeling. So this is giving us some kind of 5-manifold triangulation. So really the question is, if we just consider this single dodecahedron, what sort of triangulation is it giving us if I'm not gluing anything on the outside of the dodecahedron to anything else, just purely that dodecahedron? What is the outer triangulation going to be? And it turns out that the boundary is a copy of S4. So luckily for us, because the boundary is 4-dimensional, we can take that boundary and put it into Regina, and it will allow us to figure out what it is. So it's S4. And then a nice subdivision that Stefan did. So you can take all the 5 simplices and chop them all up into 3 5 simplices. And this shows us that we have a 5 ball because we've got this kind of coning with an S4 boundary. So it turns out that this outer triangulation is a 5 ball corresponding to this dodecahedron. So we haven't glued anything on the outside of the dodecahedron yet. So we've got a 5 ball. And so if we glued it all up with the identity gluing, as you saw in the animation, we get the 5 sphere. And it turns out that when we're doing this sort of branch covering that we were just talking about before using the dodecahedron, so we're taking S3 and we're branching over the Borromean rings, in the outer triangulation, that corresponds to S5 branching over 3 copies of S3. Okay, so this is a really, it worked out quite conveniently. So down here, this line over here, this is corresponding to the branch covering of S3 over the Borromean ring. So here is our 3-manifold, which is our central 3-manifold. And then upstairs here, we have the corresponding 5-dimensional outer triangulation of S5. And we're branching over 3 copies of S3, each corresponding to one of the components of the Borromean rings to give us this 5-manifold. So this is our result with Stefan Tillmann. The triangulation W5 is a manifold, and in particular, every closed orientable 3-manifold is the central submanifold of a trisection of a piecewise linear closed orientable 5-manifold. So what do those 3 copies of S3 look like? Well, we can almost entirely read them off the labeling of our cubing, because a whole bunch of it turns out to correspond to the edges of the Borromean rings, which live on the dodecahedron that we were talking about before. So the segments, those half segments of the components of the Borromean ring correspond to 4 edges on the cubing. And those 4 edges correspond to 4 tetrahedra. So we've got 8 tetrahedra corresponding to those Borromean rings, which we have over here, but there are some hidden ones which only have 2 colors, so they're not immediately visible. So this one over here, for instance, and this one, and this one, and this one, and so forth. So we get these 3 spheres that the components of the Borromean rings live inside. They live inside these things. And we're branching over these 3 copies of S3 in our S5. So what does the preimage of this branching over these 3 copies of S3 look like in S5? Well, here's an example. So here's the choice of branching here that I've got. We've got the meridian A mapping to this element and so forth. And if we look at the group that's generated by A, B, and C, it's this group over here. And the 3-manifold, according to Regina, is this ciphered fibered space. And so the preimage of those branching spheres are all of these spheres over here. So the purple ones correspond to A, the orange to B, and the blue to C. So you can see that in this example, these are kind of, they correspond to components of the Borromean rings upstairs that are sort of as small as they can get. But this one, see, is kind of like double the size, because you can imagine those segments of the Borromean rings, they're gluing up in a certain way. So some of them can be very big and some can be very small. And also, for instance, this one over here, this is like a degree 4 branching here over the dodecahedra that are labeled 1, 6, 4, and 5. So this one over here is kind of the degree 4 branching that's corresponding to this part here. All right. So also it turns out that after we perform a collapsing of the central vertices of the outer manifold, it turns out that there's this one-to-one correspondence between the vertices of the outer triangulation and the vertices of the central submanifold. And this allows us to show that the fundamental group of the central submanifold is isomorphic to the fundamental group of the outer manifold, which is quite a fun result. So that's quite convenient for us. So the way I kind of I think of this is that this outer triangulation is kind of like a thickened up 3 manifold, because they have the same fundamental group. So it might turn out that they have the same higher homotopy groups. I'm not sure about that. But it's kind of like a thickened 3 manifold. So here are some examples. So here's a branch covering with A being sent to 3, 4, 1, 2, B to 3, 4, 1, 2, and C to 1, 3, 2, 4. It turns out that the central submanifold here is RP3. So you can see, for instance, A, you notice that 1 is being sent to itself, and that's why we have here in 1 that these are both colored green, because it's just shutting up like this. And then, for instance, with 3, 4, if we look at 3 and 4 in terms of A, notice that this red is going to this one over here. So it's going, the 3 is going to the 4, and then again, this 4 is going to this 3. So you can see this kind of order 2 gluing. And so, okay, we know what the central submanifold is, but what will the outer triangulation be? Well, what we can do is we can remove these gluings. So if we remove all the gluings I have here colored, this is going to give us some kind of manifold of a boundary. So what will it give us? It turns out that when we remove these gluings, we get a copy of B5. So we get a 5-ball. So this is not, I'm not responsible for this really. I sort of, this is another one of Stefan's students, wrote some code using discrete Morse theory. And it's meant to work only for simplicial complexes, but I tried it with this example and miraculously it worked. So discrete Morse theory is the discrete version of Morse theory. And the idea is that you want to take a triangulation and get some kind of flow on it to do a whole bunch of cancellation to get these things called critical cells. And if there's only one critical cell by Whitehead's theorem, this tells you that this thing is B5. So this is very convenient. So I'm very grateful for that student's work. Yeah, so if you zoom in, so you have to believe me that if you zoom in over here, that there is only one critical cell. So what do we do with that boundary though? We've removed things, but we have to put them back in if we've removed them. And it turns out that that boundary, which is S4, if you put everything back in, it's an antipodal gluing. So you can see here from the color choice from the previous slides. So for instance, this purple over here is mapping to this purple over here. So this is an antipodal gluing of S4. So this is showing us that we have this 5-ball with an antipodal gluing on its boundary. So this shows us that this is RP5. Okay, well, maybe let's have a look at some central submanifolds, because we've been talking a lot about how they're cubings, but what do those cubings actually look like? Well, luckily, Regina and a bit of programming allows us to see what they look like. So here is the identity So as we were talking before, that picture of, you know, of the dodecahedron and gluing everything up using the identity branching. So using our cubing, this is the cubing of the 3-sphere. Here is a cubing of RP3. Here is a cubing of RP3 connected sum RP3. Here is the ciphered fibered space. Here's another one, and another one. And this one I like a lot, S2 cross S1, because you can see some 5-order symmetry over here that's coming hopefully from this, and some order 2 symmetry as well. Thank you very much.
I'll get everyone to unmute and clap if you can. Carol, those last pictures, I think that it was lagging a little bit. So
oh, sorry.
I for one would like to look at them a little bit more.
Yeah, sorry about that. I'm on my phone internet. It's not ideal, but hopefully I'll slow it down. Thank you. I kind of see like a bird flying in this one.
In which direction?
Like this. But I don't know.
Yeah, I see it. It's going up.
But hopefully, yeah, please tell me if I'm going too quickly. So this was, part of this was done with Mathematica. I've become a really big fan of adjacency matrices. So I was making a lot of adjacency matrices in Regina. It's a really convenient thing to do. Like, if this condition is true, then this entry in this matrix is 1, or whatever it will be, you know. And then if it's not true, the entry in this matrix is 0. And then you take that adjacency matrix, you put it in Mathematica, and it gives you a nice picture. And what I think is fun, because Regina is in Python, so I'm interested now in like I don't know what you'd call it. Like, it's kind of like a composite function. You make the output in Regina the input for Mathematica. So you write you print it, so it's the output designed for Mathematica, and then you just copy and paste, and then Mathematica. So I don't know what you'd call that, but I think that's a fun thing to try.
Yeah, I feel like that's something I could benefit from too. Like, I'm often using Snappy or Regina and then, yeah, doing calculations in Mathematica. Yeah. Does anyone have questions, Carol?
I've got a question, if that's okay.
What's your question?
Thanks. Sorry, I wasn't sure whether I was coming through. I didn't mean to wait for so long to ask. So earlier you had this long slide where you showed S3 minus the Borromean rings, and you had some expression for the finitely generated group that was the fundamental group. I'm not terribly familiar with these kinds of things. I was wondering, how do you know this group is, yeah, exactly this one. How do you know this group is finite?
How do I know this group is finite here?
Yeah, exactly.
Well, I'm not quite sure to check immediately. But the thing is, with fundamental groups, a lot of them are not finite. It's really, when I'm saying finite, I'm talking about G, because it's a finite branch covering. So this would, I'm assuming, is not finite, right? Because I can just take the meridian element and just keep going whizzing around, right, and raise the powers. But the important thing here is that G is finite, because it's a finite branch covering. it's very tricky. If you look at a group presentation and you ask yourself, is this finite? Is this not finite? It's very hard. Sometimes there's quite a bit of subtlety in that kind of question, because if you take a relation and you just tweak it a tiny little bit, that tiny tweak can be strong enough, a condition that sort of forces finiteness. But, you know, it is very tricky on first glance. But when you're dealing with these kinds of fundamental groups of three manifolds, typically I think of them as infinite, like, but there are some in higher dimensions, because, you know, like when you're dealing with four manifolds, I think there's a theorem like every finitely presented group is the fundamental group of a four manifold or something like that. And, you know, that's going to be true for higher dimensions. So you're going to get some weird groups. But when you're just looking at a presentation on first glance, it is very tricky to see if something is finite or not.
Okay, next, thank you.
Any other questions? So at one point you had, did you say like 120 tetrahedra or cubes or something?
Yeah, I'll this kind of thing.
This was 120 cubes.
Exactly.
Yeah, right.
And so in the
like, I just feel like that must be computationally like ridiculous to do anything with.
So really it was exhausting. Like the first step is take this coloring and this cubing and figure out what that corresponds to in the outer triangulation. So the difficulty really was, first, it was a bit of a difficulty to get to this picture, because if you're just trying naively with cubings, some cubings won't allow you to color it with three colors, you know, for all these conditions. So first, getting this kind of cubing that respects the dihedral symmetry, that was the first step. And then, so the next step is draw this picture. So this was the hard part, was kind of drawing it. It's all determined, but I guess the thing is you don't want to make any mistake. One tiny mistake and the whole thing, unfortunately, is wrong. But the thing is, yeah, so the difficulty was drawing this picture and then putting it into Regina and not making any mistake. But the thing is, because of the choice of labeling, so remember, this is one of the dodecahedra, but there's a whole bunch more, and the choice of labeling is identical, right? And because there's 120 of these things, right, in the second dodecahedron, this would be labeled 120, and this would be 121. So everything's identical. So I just have to do it mod 120.
Yeah.
But once, yeah, but once it was good, because it forced me to have to learn how to program a little bit. It's good to be forced to do things, because then, you know, it's so convenient to just, in my code, all I have to do is type in what A, B, and C are in a particular way, press enter, and it does the whole thing by itself.
Yeah, nice. Cool. Alex is appreciating everything, basically, I think.
Yeah, thank you, Alex. The symmetry, yeah, this really made me appreciate symmetry a lot, which is something I'm a big fan of. But yeah, it's all about symmetry for this to work. You need that dihedral symmetry for that coloring.
Cool. Okay, well, let's maybe thank Carol again, and we'll stop the recording, and you can hang around to socialize if you want.